We talked in the previous video about the fact that if you add thermal energy to a body of water or any other thing, one thing that can happen is it goes up in temperature. And if it's going to go up in temperature, we know that the amount of heat required is equal to the mass of the object times the specific heat times the change in temperature that is experienced. But that's not the only thing that can happen. Another thing that can happen is you could start boiling the water. The water can start changing phase from solid liquid, from yeah, from a solid to a liquid, from a liquid to a gas, or in the other direction, from a gas to a liquid, or a liquid to a solid. And in that case, it also takes energy to cause the phase change. So the amount of energy required to change a liquid into a gas is equal to the mass of the stuff times something called the latent heat of vaporization. So again, the latent heat of vaporization is a property of the material. Different materials will have different values, but this is the heat required to boil a substance. So if you're adding heat to a substance, you're going to be converting it from a liquid to a gas, you're going to be boiling it. This is also the amount of heat that is released when something condenses from a gas to a liquid. Those are inverse properties. So if it requires 100 joules of energy to boil a certain amount of water, you're going to get back 100 joules of energy when that water condenses, when that water vapor condenses back into water. And then there is the heat required to melt ice. If you want to melt something, turn it from a solid to a liquid, you need to add heat, and the amount of heat you need to add is the mass of stuff that you want to melt times the latent heat of fusion. And also, the inverse property is freezing. If you have a liquid and it's converting into a solid, it's going to release energy, and the amount of energy released, the amount of thermal energy released in that process is also equal to mass times the latent heat of fusion. So, as a simple example, I'm making this up off the top of my head. If I have a isolated container filled with 200 grams of liquid water and a 50 gram ice cube, and the ice cube starts out at 0 degrees Celsius and the water starts out at 20 degrees Celsius. The question is, what will the temperature be after all the ice is melted and the ice has reached an equilibrium temperature with the rest of the water? So again, we're going to use the idea that Q total is equal to 0 because it is an isolated system and there's no work being done to add energy to the system. And that means that the Q for melting the ice plus the Q for heating the melted ice that has now turned into water, plus the Q for cooling the water that started out at 20 degrees should equal 0. So this is going to be M times the latent heat of fusion, and this is going to be a positive number because we are melting the ice and it requires energy to melt the ice, plus, okay, and this is going to be, since we've got two different masses, I want to be sure to label this as the mass of the ice that we started with times the latent heat of fusion, plus now the ice has now turned into water, but it's still the 50 grams. So I'm still going to label that the 50 grams of the mass of the ice, but now it has turned into water and it's heating up. So I need times C for water times delta T, which is going to be the final temperature minus 0 degrees Celsius. Okay, plus the Q for cooling the other water. So this is going to be the mass of the water that we started with, that 200 grams, times the C for water, the specific heat of water, times the change in temperature, which is going to be T final minus 20 degrees Celsius. And when we add all those up, we should get 0. Okay, so this is 0.05 kilograms, and I have to look up the latent heat of fusion for water. Okay, let's see. There's water, and here is the latent heat of fusion for water is 334,000 joules per kilogram. That's a lot. Okay, plus the mass of the ice, that's 0.05, times the specific heat of water, which we decided in the previous problem was 4186, times T final, and I'm just going to drop the minus 0, plus the mass of the water, 0.2 times 4186 times T final minus 20 degrees Celsius equals 0. So let's start to do this. 0.05 times 334,000 is 16,700 plus 0.05 times 4186 is 209.3 T final plus 0.2 times 4186 is 837.2 T final minus 0.2 times 4186 times 20 is 16,744 equals 0. Okay. So then it looks like 209.3 plus 837.2. This is 1046.5 T final is equal to 16,744 minus 16,700, which is 44. So then 44 divided by 1046 says that T final is 0.042 degrees Celsius. So what happens is that the amount of heat required to melt all the ice was just a tiny bit less than the heat required to drop the water all the way down to 0. So we almost dropped the water all the way down to 0 degrees, but not quite. So that amount of ice in that amount of water is almost enough to completely cool all of the water. Now, if we'd had even more ice, what would have happened is we would have gotten a negative temperature, which doesn't make sense because you can't have a negative temperature if you melt all the ice. And so instead, we would have to ask the question, how much ice is left once you get the water down to 0 degrees? And that would be a slightly different problem. But we would set it up the same way, except this amount of ice that melts would be unknown. This term would be equal to 0 because the final temperature is 0 degrees, and this final temperature would be 0 degrees. We would know what the final temperature is and would be solving for the amount of ice that melted. That would be a slightly different problem, but it would be an interesting problem. Okay, that is the end of this video.